Hello everyone, and thank you for joining this webinar. My name is Michael da Costa Carneiro, and I am a product manager at Xena Networks. Today I'll be talking about what you can do with an Ethernet impairment emulator and how it can be used to improve 5G fronthaul testing. At the end of the presentation, I'll briefly tell you about Xena Networks' own Ethernet impairment emulator called Chimera. Today, I'll first talk about what is Ethernet impairment emulation and explain why we at Xena Networks consider it an important part of testing your Ethernet device or application. Next, we'll share our experience from working directly with customers and describe how an Ethernet impairment emulator can be used to improve testing of equipment for the 5G fronthaul networks in the convenience of your own lab before it's deployed into the real world. We'll start by taking a look at what's new in the 5G fronthaul network compared to previous generations of the fronthaul, and then we'll take a look at what to impair and how to impair. Finally, we'll talk about two timing issues which you need to be aware of when using a network emulator in the fronthaul, due to the very strict timing requirements imposed by 5G applications. At the end of the presentation, we'd like to tell you a little about our new Xena Network Impairment Emulator called Chimera and how Chimera can help you improve fronthaul testing. Following the presentation, we'll open up for a questions and answers session. So first, let me talk about what is Ethernet Impairment Emulator, what can it do, and why do we need network emulation in the first place. Imagine a test setup in the lab where you have two devices under test directly connected across an Ethernet cable. In this setup, you can of course do a lot of testing of protocols performance and evaluate the user experience of your application. But what really happens when the same devices are connected across a real live Ethernet network, introducing random impairments like variable packet delay, occasional packet drops, corruption, or even failover due to links becoming unavailable? Depending on your application, these networking imperfections can have huge impact on how well your application is perceived by the user. So it's an important part of the product testing to try out your application in a realistic environment. However, when testing in a real Ethernet network, such impairments can be very difficult to control, thus making it difficult to do well-defined and repeatable testing of your device or application. And this is apart from the fact that testing in real-world networks can be both expensive and very time-consuming. An Ethernet network impairment emulator is a drop-in replacement for the network connecting the two DUTs, which acts as a bump in the wire. The network impairment emulator allows you to map the incoming packets to different packet flows using flow filters, based on the packet encapsulation. The first question we need to ask ourselves when using an emulator is what to impair in terms of the packet encapsulation. The packet flows to be impaired can be based on a VLAN value or on more specific message fields, as we shall see for the eCPRI later on. Once they're defined, the impairment flows are forwarded to separate impairment pipelines, where each flow is individually impaired. Now the second question we need to ask ourselves is how to impair. That is, how to configure the impairment pipeline of each of the defined flows. Impairment could start by dropping 1% of your data frames and then later increase this to 10%, or let you delay your control frames with a fixed delay, which can then be increased as you measure the performance degradation of your application. The setup of the impairment module must of course support scripting of all commands for easy automation and provide relevant statistics to be used for automated test result evaluation. With the increasing data rates of today's networks, it's important that the network impairment emulator will do wire speed emulation of all speeds that your equipment supports in a single box, including ports speeds up to 100G. So in short, if you can define the flows that you want to impair in terms of the network encapsulation and how you would like to impair selected flows, the Ethernet Network Impairment Emulator will allow you to do repeated testing of well-defined impairments to the selected flows, providing the exact statistics you need to evaluate your application. So why do we need Ethernet network emulation? Well, for many years, there's been a transition in the networking world, moving away from traditional circuit switched networks and leased lines towards more general Ethernet packets networks. And the reasons are obvious. Ethernet scales very well. It allows for statistical multiplexing. It supports virtual network functions like software-defined networks and network function virtualization. And there are many vendors of Ethernet equipment selling good commercially off-the-shelf COTS products, and interoperability between vendors is generally good. And actually, the advantages of Ethernet I just mentioned are among the main drivers behind upgrading the 5G radio access network, including the move to using eCPRI in the 5G fronthaul networks, as I will talk about in a couple of minutes. But first, all good things come at a price. Legacy circuit switched networks provide easy end-to-end timing, predictable behavior, very low jitter, and very well-defined bit error rates. In turn, moving to Ethernet-based networks implies living with the potential packet drops, significant jitter, and other imperfections such as misordering and packet duplication. For many years now, we have been adding these missing features to Ethernet. This includes end-to-end synchronization with protocols like PTP and SYNC-E, or adding OAM capabilities to carrier-grade Ethernet as specified by ITU-T Y1731. The results are good, but not good enough to hide the nature of the underlying Ethernet-based network. So in order for us to design well-functioning and robust equipment and end-to-end applications, we need a way to test the effects of Ethernet impairments before doing actual implementation in a real-life network. Even more so, because ordering an Ethernet connection today involves more than just buying sustained data rate and uptime. You need to agree with your service provider on a service level agreement, or SLA, which specifies limits to latency, jitter, packet loss, guaranteed failover times, and much more. So how do you know which SLA to purchase, and how do you know if your equipment or networking application is robust enough to run on the network you have, and whether you have enough margin in your design to function properly when the network performs at its worst, which might only happen very rarely? One obvious answer is to move the Ethernet network into your lab in a very well-defined and controllable manner using an Ethernet network impairment emulator. So returning to the question, why do we need Ethernet network emulation? Here at Xena Networks, we believe that the best way to test the equipment or applications is to include real-life conditions in the product development and testing by adding a network emulator. So what should we test? We need to test how the real-life conditions affect our application's performance and whether we have enough margin to give our users a good experience even if the underlying network is operating at the border of our SLA. And how can we do this? Using a network impairment emulator, we can point out exactly which flows we want to test and then apply well-defined and repeatable impairments to these flows, while other flows pass unhindered through the emulator. Scripting will make it easy to automate the testing, and selecting a single box which can do wire speed impairment at all speeds supported by your devices will give you an easy way of testing your devices under maximum load under all given circumstances. So essentially it all boils down to two questions: what to impair and how to impair. In the following, we will help you answer these questions using the 5G Fronthaul as an example. So now, let's take a look at the 5G Fronthaul to see how we can use a network impairment emulator to test the protocols controlling the interface to the antennas in the remote unit. Due to the extensive technical changes, the transition to 5G requires a new network architecture. These new networks will be required to adhere to strict timing, latency, and availability requirements, so extensive testing will be the key to assuring the expected end-user experience. This slide illustrates the main differences in the 5G fronthaul network compared to the previous 4G fronthaul. In the illustrated network, data to be transmitted on the antennas is running from the core network at the left side of the slide towards the antennas illustrated in the right side of the slide. while the data received on the antennas run in the opposite direction from right to left. For simplicity of this presentation, I will focus on the transmit path, but basically the same arguments apply to the receive path in the opposite direction. The transmit path is referred to as the downlink direction in the O-RAN specifications, while the opposite direction is referred to as the uplink direction. Data from the core network is sent from the central units, or CUs, to the distributed units, DUs, via the backhaul network, while the DUs transmit data to the radio units over the fronthaul network. The RUs in turn control the transmission on the antennas. One major driver behind the design of the 5G wireless network is to move away from the proprietary protocols running on CPRI in the fronthaul of today's 4G networks, as well as the CPRI protocol itself, because it typically runs on dedicated fibers, which is inexpensive, inflexible, and it does not scale very well. Another important driver is the ambition to build the 5G fronthaul elements on COTS hardware, and with standardized protocols to allow operators greater flexibility when building their networks. One example of such an initiative is the O-RAN Alliance, backed by many equipment manufacturers, network operators, and telecom companies. To support these trends in the 5G fronthaul network, the CPRI is being replaced with eCPRI running over standard Ethernet. As mentioned in the introduction, moving to standard Ethernet gives great flexibility and supports virtualization functions like software-defined networks and network function virtualization, but causes the pain of having to live with more unreliable network and having to do end-to-end synchronization over Ethernet. In the 5G fronthaul networks being implemented today, RUs are designed with 4, 8, or even more Ethernet interfaces running at speeds of 10G or 25G. So a high port density is required to test simultaneous use of all interfaces. For completeness, I should mention that eCPRI can be replaced with radio over Ethernet as specified in IEEE 1914.3, but I will focus on eCPRI transport in this presentation. In the 5G fronthaul, end-to-end timing is particularly important because antennas have dedicated transmission and reception windows which need to be coordinated with adjacent antennas to avoid interference. To add to the importance of the timing requirements, the exact transmission timing of the antenna is determined by the DUs, each controlling a number of antennas. Looking at the way the network is built, it's quite obvious why significant jitter on the eCPRI interface will complicate controlling the antennas from the DUs, and how loss of data or control frames will influence the user experience for users connected to the antennas from mobile devices. Keeping in mind that the extent of the fronthaul networks range from a few kilometers to up to 50+ kilometers underlines that the design challenge of these networks is indeed significant. Because 5G networks are large installations, they are costly to design, build, and operate. It is important to test the robustness of the entire installation before it's installed and put into operation. One way of making sure that the design from the DUs to the RUs is robust for the imperfections of Ethernet fronthaul network is to replace the fronthaul network with an Ethernet emulator to do well-defined testing in the lab before rollout. So, to better understand what we need to test, let's take a closer look at the protocols running in the fronthaul network. In this slide, we'll take a closer look at the data being passed between the distributed unit and the radio unit over the 5G fronthaul network, as defined by the O-RAN Alliance Fronthaul Working Group. The O-RAN specification defines a complete separation of the control plane and the data plane. The U-plane transports all data IQ samples to be transmitted on the antennas. As the slide shows, U-plane data is transported across Ethernet with optional VLAN tagging and optionally transported over UDP and IPv4 or IPv6. We'll look closer into the details of this in the next slide. The C-plane transports the control information regarding the real-time control of the current connections. The main purpose of the C-plane is to transmit data-associated control information required for processing of user data, for instance, scheduling and beamforming commands. The C-plane supports the same encapsulation options as the U-plane. To assure the separation of the C-plane and the U-plane traffic, the two flows must use different VLANs, DMACs, or UDP ports. Because the C-plane and the U-plane relates to the same channels, there are strict timing relation between them, as we shall talk about later. As mentioned earlier, there are very strict timing requirements for the entire Fronthaul network. ORAN specifies the S-plane to take care of synchronization. The S-plane describes how to use PTP and SIG-E to achieve very tight synchronization across all networking entities in the Fronthaul. S-plane traffic is transported using native Ethernet. Finally, the ORAN Alliance specifies the M-plane for management of the Fronthaul system. The M-plane handles the setup of the DUs and the RUs, the configuration, as well as functions like fault handling, statistics, and file management. There are two options for the location of the management entity controlling the M-plane. It can either be an integrated part of the DU, or it can be an external network management system controlling both the RU and the DU via separate external interfaces. We'll not look further into the M-plane in this presentation. Next, we'll take a closer look at how to identify the flows that we want to impair to answer our initial question, what to impair. In this section, we'll take a closer look at the encapsulation of the data in the Fronthaul to understand how to configure the impairment flow filters of our Ethernet impairment emulator. Further, I'll talk about how to impair these flows, which means how to configure the emulator impairment pipelines discussed in the introduction. Here we can see the U-plane and the C-plane encapsulation when transported over either native Ethernet, including VLAN, or over UDP and IP. At the top, we can see the encapsulation when ECP is transported natively over Ethernet. For this purpose, the IEEE has assigned ether type AEFE. This illustration includes a VLAN, but as stated earlier, this is optional. However, keep in mind that the VLAN is one option for separating the C-plane and the U-plane data. Below, we can see the encapsulation when ECP is transported over UDP. In this scenario, the UDP ports depend on the implementation and can be used to identify the different data flows. This also includes an optional VLAN. So, if we just want to impair all packets of a given U-plane or C-plane, we can define our emulator flow based on a VLAN, an IP address, a UDP port, or all of the above. However, if we want to do impairment at a finer granularity, that is, if we want to impair a specific ECP flow or impair only selected ECP messages, we need to look into the ECP header itself, which is part of every C-plane or U-plane packet and located right after the ether type or the UDP header. The ECP transport header includes fields identifying the message type and the specific C-plane or U-plane flow. So, if you want to impair only certain message types, you can define your impairment flow based on the ECP message field shown here. This will allow us to impair only data messages, control messages, or one-way delay measurement messages. Alternatively, if you want to impair a certain C-plane or U-plane flow, you can define your impairment flow based on the ECP real-time control ID for C-plane or IQ data transfer message series ID for the U-plane shown here. So, once we've decided the flow we want to impair, we can specify the flow encapsulation and configure the flow filters in our impairment emulator. The next step is to decide what we want to test, so we can decide how we want to impair the selected flows. One obvious impairment to test is the variable delay of the Fronthaul network and its impact on performance due to the tight timing restrictions that apply. To better understand this, let's take a closer look at the transmission of U-plane data from the DU to the RU in the downlink direction. This slide illustrates the DU connected to the RU over the Fronthaul with the antenna located to the far right, indicated by RA. Once a channel has been configured and the transmission of data has started, it's given exactly at which time the data of each symbol to be transmitted must be present at the antenna. Given the variable transmission time over the Ethernet Fronthaul network, the RU must implement a certain amount of buffer to hold the data from it arrives at the RU till it needs to be transmitted. However, the buffer size must be limited to avoid unnecessary complexity in the RU. Given the minimum and the maximum delay of the Ethernet Fronthaul network, the size of the buffer in the RU, and the transmission window in the antenna, it's possible to define a transmission window which defines the limits for when data must be transmitted from the DU to be available for transmission at the antenna at the right time. If data is transmitted too early, there's not enough buffer to store it at the RU, and if data is transmitted too late, it'll not make it to the antenna in time for transmission. In both cases, data will be lost. Separate transmission windows apply for the C-plane and the U-plane. The calculations are not simple, as illustrated with this figure from the ORAN standard, illustrating the calculations of the transmission window and the transceive window of the downlink for both C-plane and U-plane. However, it all boils down to finding the valid DU transmission window and testing that data is correctly transmitted and received at the antenna if it's correctly sent within the transmission window at the DU. In the same way as we found the DU U-plane transmission window, we can now calculate transmission and receive windows for C-plane and U-plane in both uplink and downlink directions as listed here, all of which calls for dedicated testing of the effects of the Fronthaul variable delay. As the discussion of transmission and reception windows clearly shows, the correct timing of data to the antennas rely heavily on the timing within the DU, the delay of the Fronthaul network, as well as the timing within the RU. However, the timing within the DU and the RU due to processing and buffer delays will depend on the actual implementation, and it's expected to vary between different DU and RU implementations. To help match valid combinations of DUs and RUs with actual networks, the ORAN Alliance has defined a number of DU and RU delay categories which classify DUs and RUs based on certain timing properties. The table to the left shows the DU delay categories, and the table on the right shows the RU categories. Given the delay categories of the DU and the RU, it's now possible to put a limit on the maximum latency of the Fronthaul network connecting the two. The table shown here at the bottom shows valid combinations of DU, RU, and the Fronthaul maximum latency. This indicates that if you have a DU of category H and an RU of category T, the combination will allow for a maximum delay in the Fronthaul network of 148 microseconds. So, once you know the delay categories of your RU and DU, you know to which delay limits you can expect them to work, and by that, the limits of your delay testing. Once we have this information, we can connect the network impairment emulator and sweep over the latencies to verify that our Fronthaul system is robust across the required latency range. Now that you've verified that your application runs fine within the required latency range, you can further test the robustness of your application by using your network impairment emulator to drop selected packets. Due to the very strict delay constraints in the Fronthaul, it's not possible to acknowledge message reception, so it's important that we understand how the system reacts in case of lost packets. Loss of a packet in the U-plane will generally impact only a specific symbol, while the loss of a C-plane packet is more serious, with the possibility of impacting an entire slot's worth of data. A broader impact is also possible with C-plane packet loss. If downloaded beamforming weights, beamforming attributes, or channel information is lost, then a beam ID may be incorrectly associated with an old set of beamforming weights, thereby possibly impacting multiple slots. Packet loss can be detected via sequence numbers, so recovery action may be taken to resend messages that may have a persistent impact. In addition to dropping packets, adding a network emulator to your testing will allow you to further explore whether your network or application is robust to jitter, packet corruption, misordering, or packet duplication, all things that will eventually happen in an Ethernet environment. Finally, the ORAN specification defines a set of counters and KPIs to be implemented on all DU and RU interfaces. These counters also indicate relevant areas of testing. In addition to error counters and general RxTX statistics, these counters include dedicated counters to indicate whether a packet is arriving early, late, or within the Rx window described in the previous. Separate counters exist for both the U plane and for the C plane, all of which can be easily tested using a network impairment emulator. So adding an emulator to your testing not only allows you to verify that your application will run within the latency limits of your network, an emulator will further allow you to pinpoint exactly what are the pain points of your application with the possibility to redesign in order to improve robustness. And this includes the discussion on how we can impair ECP messages in the Fronthaul. But before we're done, I'd like to talk a little about network timing. Because even though we will not be looking into testing PTP and SIG-E as part of this presentation, there are two very important timing considerations to be aware of. As I mentioned earlier, the ORAN Alliance defines an S-plane using PTP and SIG-E for timing synchronization across all the networking elements in the 5G Fronthaul. And both of these protocols rely on the support in each single networking element for proper functionality. As we've seen, the network impairment emulator will be inserted in the network forwarding the PTP and SIG-E messages, so it is important that the emulator is carefully designed to prevent that the emulator itself becomes a destructive element in the efforts to synchronize the Fronthaul. The first timing issue we will take a look at is the emulator's support for SIG-E. Going back to the overview of the Fronthaul, 5G installations rely on SIG-E for end-to-end synchronization, which is very important to allow a single mobile device to connect to several antennas simultaneously, for instance, during a handover. SIG-E allows the synchronization to be dictated by a central source, and timing information must be forwarded by all the elements of the network. Particularly, this means that SIG-E clock forwarding must be supported across the Fronthaul network. So it's important that any networking impairment emulator used for testing does support SIG-E forwarding. For instance, if we insert an element like an emulator which does not support SIG-E forwarding of the clock, it will break the SIG-E synchronization across the Fronthaul and prevent correct operation in the RUs. The second timing consideration that's important when using an emulator in the 5G Fronthaul is the contribution to unwanted jitter by the emulator. The ORAN S-plane uses PTP for timing synchronization, and it's known that the PTP protocol is very sensitive to jitter in the forwarding plane. Looking at the Fronthaul, it's clear that additional jitter will be added by every switch or network element that you add in the path between the DU PTP master and the PTP slave located in the RU. Further, an Ethernet standard switch, which is not timing aware, will simply introduce too much jitter for P2P to function correctly if inserted into the Fronthaul due to the packet jitter caused by Ethernet packet switching functions like queuing, store and forward delays, etc. So to make sure that synchronization is possible in the Fronthaul, the ORAN S-plane standard specifies that all Ethernet switches in the Fronthaul must implement PTP boundary clock or at least support PTP transparent clock functions. The standard further puts an upper limit to the number of switches to be placed between the DUs and the RUs depending on the PTP timing position in the switches. So now going back to the Fronthaul network overview, we can see that the network impairment emulator will be going right into the forwarding path of the S-plane, which means that the emulator must be timing aware or avoid introducing jitter to the PTP message flow, which will prevent required synchronization. To do this, the emulator has three options. The first option is to keep the jitter well below 30 nanoseconds. In this case, the emulator will not be PTP aware, and PTP messages will pass transparently through the emulator along with other data at a fixed delay but with very little jitter. One limitation of this solution is that the emulator will be limited to one single flow, because any modifications of the packet sequence will be impossible without introducing significant jitter. From this follows that it's not possible to test the effect of jitter on the C-plane or U-plane traffic, because the same jitter will be applied to the PTP messages. The second option is for the emulator to support PTP transparent clock. This requires the network impairment emulator to be PTP aware and to update the correction field in the PTP messages passing through the emulator. This will allow rigorous testing of the C-plane or U-plane traffic without seriously affecting the PTP precision. The final and last option is for the emulator to support PTP boundary clock. In this case, the emulator will need to run the PTP protocol and terminate the PTP flow in the uplink direction to recover the PTP clock. The emulator must then implement a PTP master clock function to provide timing to the downlink part of the network via a separate PTP flow. So with this, I've concluded my presentation on how to test your 5G fronthaul elements or applications using a network impairment emulator. And now, before we move on, allow me to summarize the main points made in this presentation. The 5G is fundamentally changing the fronthaul network to benefit from advanced technologies like software-defined networks and network function virtualization. One of these changes is introducing eCPRI over Ethernet for transporting C-plane and U-plane data between the distributed units and the remote units in the fronthaul. While Ethernet comes with a lot of benefits, it also has its drawbacks in terms of jitter, packet drop, and other networking impairments fundamental to Ethernet networks. Another characteristic of the 5G network are the very strict synchronization requirements between fronthaul networking elements, and strict timing is not originally part of the Ethernet DNA. So the O-RAN Alliance defines an S-plane using SYNC-E and PTP to achieve the required synchronization. Large networks like the fronthaul and its applications will need abundant testing prior to rollout. As an alternative to testing your networking components or applications in real fronthaul environment, which can be very expensive, cumbersome, and difficult to control, I've talked about introducing an Ethernet impairment emulator to emulate the impairments like latency, jitter, and packet drops that will occur in real-world networks. Using the C-plane and the U-plane data over eCPRI as an example, I've talked about how you can define the exact data flows that you want to impair and subsequently which impairments you can apply to these flows, illustrating the basic idea that if you can specify the data flows you want to impair in terms of the packet encapsulation and how you want to impair these flows, you can use an Ethernet impairment emulator to do the testing in your own lab. One major advantage to this approach is that the emulator will allow precisely defined automated testing to verify that your equipment or application works fine within the limits of your network. In addition to this, you can use the emulator to identify and explore the pain points of your product in order to improve robustness wherever needed, making the cycle of test, improve, repeat as short as possible. Finally, I spoke about the necessity of the emulator to support SYNC-E clock forwarding and being PTP timing aware in order not to let the emulator itself prevent the synchronization of PTP and SYNC-E required in the fronthaul network. And this sums up what I had to say about using Ethernet impairment emulators in the 5G fronthaul network. Finally, before we move to the questions and answers session, please allow me to share with you some information about our Ethernet impairment emulator called Chimera. Chimera is an Ethernet impairment emulator with two QSFP28 interfaces, supporting speeds from 10G to 100G in a single box. Chimera supports easy mapping of incoming packets to 8 flows per port and individual configuration of impairments to all flows, allowing you to carefully select which packets to impair, whether it be ECP, PTP, or other protocols in your Ethernet network. Chimera supports sync-E forwarding of the recovered clock and supports a multitude of impairments like packet drop corruption, duplication, and shaping of input and output bandwidth. Further, Chimera supports advanced distribution schemes not only for jitter, but for all the supported impairments. Chimera will even allow you to define your own distribution scheme. Please notice that Chimera will do wire speed impairment at all the supported speeds, including 100G, and has a very flexible port allocation scheme which puts no restrictions on how many ports can be allocated to each user. Chimera supports scripting for easy automation and rich impairment statistics for automated verification of testing. Chimera comes in two hardware flavors, either as a standalone 1U module or as a PCIe module that can be mounted in a Valkyrie bay, allowing up to 48 25G ports or 12 100G ports in a compact 4U chassis. And last but not least, we are currently working with customers to test their applications in the 5G Fronthaul using Chimera as their Ethernet impairment emulator. So whether you're an equipment manufacturer or a network operator, Chimera offers the most cost-effective way of testing the performance and conformance of your networks, services, and applications. This concludes this presentation. So now let's go on to the questions and answers session. Thank you for listening.